Welcome to the principles of infrared spectroscopy. Let's get started right away with probably the most important question. What is infrared spectroscopy? Basically, infrared spectroscopy studies the interaction between infrared radiation and matter. We might end this presentation right here, but you may ask, what is infrared radiation? Well, infrared is a particular part of the electromagnetic spectrum that has a longer wavelength than visible light. A longer wavelength means the light carries less energy. A longer wavelength also means a smaller wave number. Since infrared spectra are mostly labeled in wave numbers, wave number is a term frequently used throughout this tutorial. All infrared spectroscopy is not created equal, as it can be subdivided depending on wavelength into near, mid and far infrared, although mostly mid-infrared is meant when the term IR spectroscopy is used. As mentioned before, infrared light interacts with matter. But how exactly? Well, first infrared light passes the sample, in our case an exemplary water molecule. Depending on the energy levels, this light can trigger vibration in specific molecular bonds. This is called absorption. There are different kinds of vibrations, but the most prominent are the symmetric stretching vibration, the anti-symmetric stretching vibration, and the deformation vibration. Others are rocking, wagging, and twisting vibrations. The energy absorbed by the molecule is consumed and is therefore missing from the original IR beam. But how can we use this principle to our advantage and investigate this interaction? First, we need infrared light from a fitting source. The light is then directed at the sample. Some light is going to be reflected, but a larger fraction will travel through the sample and specific parts of it are going to be absorbed by the sample material. The part of the light that is transmitted and carries the molecular information of the sample can then be collected by a detector to produce an electronic signal. But how do we turn this electronic signal into a spectrum? Well, this depends on how the infrared spectrometer is set up. In its early days, infrared spectra were exclusively acquired by traditional dispersive IR spectrometers. This was done by directing light onto a diffraction grating that splits the light into several single beams. Afterwards, these beams were directed at the sample and each wavelength individually examined. With the rise of improved electronics and CPU processing power, Fourier transform infrared spectrometers superseded these traditional instruments because FTIR spectroscopy offers significant advantages. It has an improved signal-to-noise ratio, it is a lot faster, and it shows superior wave number accuracy when laser calibration is applied. But how does an FTIR spectrometer differ, and how does it work? At the heart of the FTIR spectrometer is an interferometer. Shown on the right is a Michelson-type interferometer. During the measurement, the IR beam enters the interferometer and is directed at the beam splitter. As the name suggests, this splits the beam into two separate beams that are directed at a fixed and moving mirror respectively. Then the light travels back to the beam splitter, where it is recombined, causing interference, and is then directed at the sample material. That way, the spectral information of all wavelengths can be acquired simultaneously, saving a lot of time. At the end, the detector produces a raw signal of light intensity versus mirror position. But how do we get from here to the classical infrared transmission spectrum? To get nice and clean sample spectra, we have to get rid of the environmental influences that may show in our spectra, like carbon dioxide or water vapor. To do that, we first need to measure a spectrum without a sample present. This raw signal is then mathematically Fourier transformed into the classical IR plot of light intensity versus wave numbers. We now have a single channel reference spectrum. Then we insert the sample into the beam path and repeat the procedure. Fourier transformation then yields another single channel, but this time it's a sample spectrum. Then we only have to combine both spectra by dividing sample spectrum by reference spectrum, and then we have the classic view of an FTIR transmission spectrum. But what can we do with it? A lot of things, actually. An FTIR spectrum is like a chemical fingerprint. This enables chemical identification of a variety of samples and is frequently used to characterize material properties and verify known and elucidate unknown samples. It is utilized by many industries, but is especially useful whenever chemical information needs to be obtained straightforward in a short amount of time. FTIR is extremely versatile depending on your spectrometer setup and measurement technique used. Various applications are feasible and many different analytical questions can be answered. Thanks for watching, and if you want to know more about FTIR spectroscopy, take a look at our hands-on tutorials.